This is CHUMP Part 4 EEPROM. So I have pin 12 tied to ground, 24 to VCC. I have address pins 4 through 10 tied to ground, since we're only using address pin 0 to 3, which corresponds to values from 0 to 15, which is 16 total address pins. So it's 16 total address values. My 4 remaining address pins are tied through these blue wires to the Arduino. My digital input-output pins, 0 through 7, are tied through the black wires to Arduino. My output enable and write enable pins are tied through these yellow wires. And my chip enable pin is tied to ground, since chip enable is an active low, and we want the chip to be enabled at all times. So here's the code we're using. It begins with an array of the code, which we wrote in the first section of the CHUMP code. So this is an array, and we define the program size as the size of as many cells as there are in this code array. We declare all of our I/O pins, all of our address pins, and our write enable and output enable pins. We declare all our address pins for output. We begin the serial monitor at 9600 baud. And the code is initialized by printing the data that needs to be flashed to EEPROM. So it runs as many times as there is bytes of code in the code array, and adds 1 to each address as you go through, and it will print the code at that address in hexadecimal. Moving on, it will print writing to EEPROM, and it will run as many times as there is bytes of code in the code array. And so write EEPROM, we call it the write EEPROM function, which is here, which writes the output enable low, write enable high, since we will be writing to it, and then we'll digital write the output enable high. Moving on, we will declare each of the pins from D0 to D7 as output, since we're writing to EEPROM. So all these black wires will be outputting values to these digital I/O pins. Then, in order to write the data, we'll take the data in the code section, and we will AND it with a hex 80, which is a 1 in bit 7 and a 0 everything else. So if this was my byte of code here, and I ANDed it with this 1, it would produce a 0. It would produce all zeros. And once we do that, we will shift data left 1. So if we shift this data left 1, it becomes this with a 0 in the lowest order bit. And this 1 ANDed with this 1 will produce a 1 in D6. And this will continue until all of our code is zeros, which is why it's called destructive code, because after this, all the data is gone. But the data is now reflected in my IO7 to IO0 pins. Then we'll digital write enable low, delay, write it high again, and then delay again. After we write to EEPROM, we want to make sure our code worked. So we'll read from EEPROM. So in order to read from EEPROM, we write D7 and D0, all the pins from D7 and D0, all as inputs. And essentially what we do here is it's kind of the inverse of what we did before. So what this means is we'll take the value. So we'll take the value at D7 and add it to our original value byte. And then we'll take what's in D6 and add it. And as we continue, we'll shift the bits over one by one until we have the full data reflected across pins IO7 to IO0, with IO7 being the highest order bit. And in totality, the code should print what we're writing to EEPROM, then it writes it, and then it will read EEPROM and print the exact same thing as we put into it. So here's my adapted code. In the code array is the code I wrote in CHUMP Part 1, and it's also up here. As well, I added in all my pin declarations and all the other filled in parts. So if I go into my serial monitor, so if I write to EEPROM, it'll tell me here's the data to be flashed to EEPROM, and then we'll show what's being written, and then we'll read it. So hopefully what's being written will be reflected in the read. So 5, 61, 61, A1, A1, C, 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 C. Awesome, so it looks like it's working.